Hello and welcome to this video lesson on ligand substitution reactions, specification reference 3.2.5.2. And as you can see from the title, ligand substitutions usually result in a colour change. Here we have our lesson objectives as usual. First one being, what is the effect of size of the ligand on the substitution reaction? So are the ligands of similar size or very different sizes? And what effect does that have on the substitution reaction? Next, what is hemoglobin? And then closely related, how is oxygen transported in the blood? Lastly, what is the chelate effect? So they're the four things we're going to do in this video lesson. We're going to start off with the size of ligands on the substitution reaction. Well, first of all, what do we mean by ligand substitution reactions? Well, all we mean is that for a given complex, when the one ligand is swapped out for another ligand, that is a ligand substitution reaction. Firstly, let's consider similarly sized ligands. An example of that would be a water ligand and an ammonia ligand. So let's just write those in, H2O and NH3. They are both of similar sizes, and when either ammonia substitutes for the water molecules or vice versa, the point is you get no change in coordination number. That's the number of coordinate bonds attached to the metal ion, and you get also no change in shape either. And so an example of such a reaction would be, well, actually before we do that, the other thing we'll consider in due course is differently sized ligands, and then partial substitution of ligands. So when some of the ligands are replaced and some of the ligands are not replaced, we'll consider those as well. But going back to the similarly sized ligands, we have this as our example. As I said, we've got water and ammonia as the ligands, and let's start off with this cobalt complex, and it's got 6 water molecules coordinately bonded to it in an octahedral shape. So the coordination number, let's summarize that by just calling it Cn. Coordination number is 6. As you can see, 1, 2, 3, 4, 5, 6. Coordination number is 6, and you can see the octahedral shape. So you've got a square planar shape for 4 of the water ligands coming into and going out of the screen. And then vertically you've got another 2 ligands, another 2 water molecules making up the octahedral shape. And so that shape is octahedral. Like that. And when those water ligands are replaced by ammonia ligands, so each one of them is now an ammonia ligand, you still have the octahedral shape and you still have the coordination number of 6. So coordination number is still 6, and the shape is still octahedral. The only thing that has changed, and this always happens pretty much, is the color change. Whereas this one is pink, cobalt complex with water ligands is pink, and a cobalt complex with ammonia ligands is straw colored. So that color change is the only change that happens when the ligands are of similar size and one swaps out the other. Sorry, one last thing to say on this is they're both uncharged. The water and the ammonia ligands are uncharged. So moving on to the situation where the ligands are of different sizes. In this case, as you might imagine, you do get a change in shape and you do get a change in coordination number because evidently the bigger ligands, you can't fit as many of those around the central metal ion as you can the smaller of the ligands. So here's an example where we've got copper complexes. On the left we have water ligands, which are quite small molecules, compared to on the right we have chloride ions, which are larger than the water molecules. All right, so we're going from small ligands, water, to larger ligands, chloride. And as you can see, we've got a coordination number of 6 for the cobalt aqua complex, whereas the cobalt chloride complex, the coordination number is 4. Fit fewer of the larger chloride ions around them. So not only has the coordination number changed from 6 to 4, our shape has also changed. So on the left with the water ligands, you can see that that is still the octahedral shape. Whereas on the right hand side, this is tetrahedral. That's a tetrahedral shape. And what's also changed is the colour, whereas the cobalt water complex is pink and the cobalt chloride complex is straw coloured. So all three things, the coordination number, the shape and the colour, all change when the ligands are of different sizes. And lastly, let's consider partial substitution of ligands. And partial substitution might happen when you only add a smaller amount of one of the ligands, and so there's not enough of them to fully replace all of the ligands. So an example of that would be this reaction here, where on the left we've got a copper aqua complex with 6 water ligands, and we've added ammonia to that, and you're going to get a complex that's got a mixture of 4 and 2 ammonia and water ligands, and the 4 water molecules that have been displaced by the 4 ammonia molecules appear on their own over here. So that's our example. Let's consider the features. This copper aqua complex here has an octahedral shape, and it is pale blue coloured. Whereas our complex that has both ammonia and water ligands is also octahedral, but it's elongated octahedral, slightly different shape, a longer shape. And instead of being pale blue, that is actually deep blue coloured. And this actual reaction here, the one that we are featuring, happens when you add an excess of ammonia. Otherwise you get a different, if you add too little ammonia, you actually get a different complex with water and hydroxide ligands. So just to summarise, we've had a change in shape, and a change in colour, but our coordination number is the same. So there we have it. That's what you need to know about ligand substitution reactions. And we're going to have a look at a particular ligand substitution reaction now, which involves respiration. Now you might know that hemoglobin is the molecule that is used to transport oxygen around the body. So we're going to have a look at that in some detail now. And firstly, I think we should draw out the hemoglobin molecule. Let's start off. You know, I think, that hemoglobin is all about iron, all right? And so the central metal ion is an iron 2+ ion. And first thing you get is what's called a porphyrin ring around it, which is where you get. Let's change colour. Let's do the nitrogens in green. Porphyrin ring is where you get a ring of 4 nitrogens coordinately bonded. So these ones are coming out of the page into from the back of the page into the iron molecule. So we've got 2 nitrogen atoms there, and then we'll draw little wedges to indicate these ones are coming from us into the page. And got another 2 nitrogen atoms there, and these nitrogen atoms, let's put our arrows on just to be complete. So these 4 nitrogen atoms are part of a multidentate ligand, but this part of the molecule now, let's draw a little ring around it like this and label it. So we've got, this is called a porphyrin ring. And this part of the molecule here is the heme part of the molecule, with the iron and the porphyrin ring. And this porphyrin ring is supposed to be horizontal, going into the page and coming out of the page. But iron likes to have 6 coordinate bonds attached to it. And so one of the other coordinate bonds is going to come from below in the plane of the screen. And this is going to be another protein molecule. I'll only draw the nitrogen atom, the protein molecule, and this is a protein molecule called globin. Put that in brackets just to indicate that it's, the nitrogen atom is just one atom of a big molecule that is a globin molecule. And so that coordinately bonds from underneath the ion, and the 4 nitrogen atoms there, as I mentioned before, are part of a big multidentate ligand as one molecule. But as I said, you've got the iron wants 6 coordinate bonds attached to it, and so there's space for another one here. So this other one here, and this could be either water. All right, so let's switch colour. Let's draw water in red for difference. So you've got waters, one of the water's lone pairs, the other 2 hydrogens. So that could be the final coordinate bond, the final 6th coordinate bond, and that would make up the octahedral shape. And this happens in the cells where there is an excess of water because it's being produced by respiration, which is what happens in the cells. So when there's an excess of water, the water molecules are in high concentration and they form a weak coordinate bond with the heme molecule. So that's in the lungs, in the cells rather, where water is in excess, like that. But let's change colour again. Let's go to purple. Instead of having a water molecule, you might just have an oxygen molecule, so it's O2 molecule with its lone pair instead. And that makes a coordinate bond with the iron, and that happens when oxygen is in high concentration, and it's in high concentration in the lungs, like that. And so just going through that process, in the lungs you've got the blood in the capillaries surrounding the lungs has hemoglobin molecules, and they're waiting for an extra coordinate bond. Oxygen is in high concentration, so it makes the coordinate bond with the hemoglobin molecules, and their blood then transfers itself to the rest of the body and finds its way into a cell where oxygen has been used up by respiration and is therefore in low concentration. So the oxygen unbinds from the hemoglobin molecule and takes part in respiration. And what takes its place is something that is in higher concentration. And as you know, water molecules are one of the products of respiration, so in the cells they're going to be in higher concentration, so they attach instead to the hemoglobin molecule. And then the blood transports them back from the cells to the lungs, where that process can be repeated and the water molecule can be expelled in your breath, and then its place is going to be taken by a fresh oxygen molecule that you've breathed in, and the whole process is repeated quite nicely. So as you can see, the process of respiration is a ligand substitution reaction, with the two ligands being oxygen molecules and water molecules. And the last thing to say about this hemoglobin molecule and oxygen transport is about carbon monoxide poisoning. And in order to do that, why don't we just draw out our hemoglobin molecule again. And so we've got our multidentate ligand, in our porphyrin ring. This multidentate ligand, of course, being one different protein molecule, and that there has formed our heme. Then we've got our globin molecule, which bonds to the heme part of the molecule by a coordinate bond from a nitrogen atom. So that's our globin, and together they're called hemoglobin. And when we get carbon monoxide poisoning, let's just write a little subtitle here. Carbon monoxide poisoning. What happens is that you get a carbon monoxide molecule which has a lone pair on the carbon. So carbon has got a lone pair and it's got its oxygen, right, and that forms a very strong bond with our iron. And because that bond is so strong, I'll write that out just so you remember it. Strong coordinate bond. So because that coordinate bond is so strong, what that means is that oxygen can't bind to that iron, and therefore can't be transported around the body. And so that will lead to things like dizziness or even death because of oxygen starvation, because your carbon monoxide molecule is blocking out the space that wants to be occupied by the oxygen molecule. So there you have it, there's carbon monoxide poisoning, and that, I hope, explains what hemoglobin is and also how oxygen is transported around the body. And our last lesson objective is to understand what the chelate effect is. And the chelate effect is to do with the reversibility of these ligand substitution reactions. So the reversibility of the reaction, so if one ligand replaces another, how easy is it to for that to happen in reverse? And that of course depends on how strong the new ligand, new coordinate bonds are. So how strong are new coordinate bonds? Right, and let's, before we go into the chelate effect, let's consider an example where the new coordinate bonds are much stronger than the ones they replaced, in which case this reversibility is less likely to happen. Okay, so we're going to consider new coordinate bonds stronger first. Okay, so an example of that would be when cyanide ligands, cyanide ions are ligands, and they could form a complex with iron 3 ions, and they could replace water ligands. So if you had an iron aqua complex that would look like this, so you've got iron 3 plus with 6 water ligands. Right, the water ligands are neutral, so our complex is 3 plus, and for completeness let's list that as aqueous. All right, and let's say we want to replace those 6 water ligands with 6 cyanide ion ligands. Then what you would get is a cyano-ion complex with 6 cyanide ion ligands surrounding the central iron 3 plus ion. Each of the side ion is 1 minus, and there's 6 of them, so that more than cancels out the 3 plus charge on the ion to leave the complex with a 3 minus charge. And then of course we have in solution we've got added 6 more water molecules. So that's an example of a reaction where the new coordinate bonds between the iron and the cyanide ions are stronger, so it's not really reversible. It doesn't really go back in the other direction. So we can say that this complex here, the one with the cyanide ligands, is more stable. Another example, let's call it example number 2, where the complex formed after the ligand substitution is more stable, is when you get multidentate ligands replacing monodentate ligands. So we'll write that out. So multidentate ligands replace monodentate. An example is given here. So we've got we're going to start off with a copper aqua complex. So you've got copper 2 plus ions, and you've got 6 water ligands, and so the complex is going to have a 2 plus charge because the water ligands are neutral. And let's say, so that obviously the water ligand is a monodentate ligand, that's the one that's going to be replaced, and let's replace it with, in this case, a bidentate ligand called ethane 1,2-diamine. All right, so if we've got 3 of those, because they're going to be bidentate ligands, so 3 times 2 is going to be 6 coordinate bonds, which is what we want to replace 6 coordinate bonds from the water molecules. So we need 3 of these molecules, and ethane 1,2-diamine has a formula like this. We've got NH2 on one end, and then we've got a CH2 group, and another CH2 group, of course, and as the name suggested, you need 2 amine groups, so you've got the other amine on this end here. So that is a bidentate ligand with one of these nitrogen atoms making a coordinate bond, and the other nitrogen atom here making the other coordinate bond. And you've got 3 of them, so you can have 6 coordinate bonds, as we said. Okay, so that those 3 bidentate ligands are going to replace our 6 water ligands, and what you're going to get is, you still got your copper, of course, and then we're just going to write in our 3 ethane 1,2-diamine molecules. So that's NH2, CH2, CH2, NH2. Right, and we've got 3 of them, all combined to our copper metal ion in the middle. And again, these ethane 1,2-diamine molecules are neutral, so our complex still has the same charge on it as the copper ion, which was 2+. And our poor little 6 water ligands have been displaced, and so they're out on their own now. And so that is an example that of a multi, in this case bidentate ligand, has replaced a monodentate ligand, and as we said, this complex is more stable, and so will be hard to reverse. Now, some of you might be sitting there asking, well, why are these 2 ligands that we've made, these 2 complexes rather, that we've made more stable than the ones we started out with? Well, in the first case, where we've got our iron, cyano-iron complex, what we've seen is stronger bonds being formed than we had in the first case. So there's going to be a negative enthalpy change. So the enthalpy change is negative. It's going to be exothermic, and that means that the product is more stable and quite likely to happen. So the enthalpy change is negative, and that's what explains the first example being more stable. But what about the second example? And for that we need to talk about entropy. And you know a bit about entropy, but a little reminder. The more particles there are means the more entropy there is. More particles needs to be entropy increase, and entropy increase means that the reaction is more likely to happen. So let's count the particles. On the reactant side, we've got 1 particle here, 3 particles there, so we've got 4 in total. And in this case, we've got 1 particle here and 6 particles here, so we've got 7 in total. So in this case, we've gone from a situation where we had 4 particles to 7 particles. So we've got more particles, so entropy is greater, so that reaction is more likely to happen, and therefore the product is more stable. And that is what is known as the chelate effect. And when you're considering the stability of complexes after ligand substitution reactions, the chelate effect is much more important because it's a larger effect than the enthalpy change effect. But to be complete, we've obviously considered both. So that completes our video lesson on ligand substitution reactions. Let's, as usual, just check we've covered everything off. And the first question we wanted to answer is what the effect of size of ligand on the substitution, and if they're the same, didn't we? So there's no change in either shape or coordination number. Only a color change, whereas if they are of different sizes, didn't we say that both the shape and the coordination number, they do change, and in both cases there are color changes. And we also covered the case where there's partial substitution of ligands. So that was the first one covered off. The second one was hemoglobin, and I'll just do that verbally. So we had an iron in the middle of a porphyrin ring, which was a multidentate ligand. And then at the bottom you get a globin molecule, also coordinately bonded to the iron. And then at the top of the octahedral shape we can either have the oxygen molecule if it's in the lungs or in the cells. The oxygen is displaced by water molecules and vice versa. So that is hemoglobin, and that is how oxygen is transported around the body. And you remember that we also mentioned that carbon monoxide blocks off that last coordinate bond so that oxygen molecules can't join with the hemoglobin molecules. So that's hemoglobin, and that's also oxygen being transported around the blood. And lastly, we spoke about the chelate effect, which is the increase in stability of new complexes that you get when more particles are created, and that's as a result of the increase in entropy because of the increase in the number of particles there. So let's just write something about the chelate effect. So let's say hash particles has increased, i.e. entropy has increased, therefore more stable complex has been made after your ligand substitution reaction, and difficult to reverse because of that increase in stability. There, all summarized in one slide. Hope that's been clear. See you in class.